Chapter 1. What is Retrieval Augmented Generation? Retrieval Augmented Generation, or RAG, is an architectural pattern that combines information retrieval systems with large language models to produce grounded, up-to-date, and domain-specific responses. At its core, RAG solves a fundamental limitation of large language models. Models do not know what they were not trained on, and they hallucinate confidently when asked about missing or outdated information. RAG addresses this by injecting external knowledge into the generation process at inference time. Instead of asking a language model to answer purely from its parameters, we first retrieve relevant documents from a knowledge store, then provide those documents as context to the model. The result is a system that is 1. More accurate. 2. More explainable. 3. Easier to update. 4. Safer for production use. RAG is not a single algorithm. It is a system design pattern. Chapter 2. Core RAG Architecture. A production RAG system consists of 5 main components. 1. Data sources. 2. Embedding pipeline. 3. Vector database. 4. Retriever. 5. Generator. Let's walk through them. Data sources. These can include 1. PDFs. 2. Markdown documentation. 3. Web pages. 4. Git repositories. 5. Databases. 6. Internal wikis. 7. API responses. Data is typically unstructured or semi-structured, which is why traditional SQL search is insufficient. Embedding pipeline. Documents are transformed into dense vector embeddings using models such as 1. OpenAI text embedding models. 2. Sentence transformers. 3. Instructor models. 4. E5 family. 5. BGE embeddings. Key principles here. 1. Chunking strategy matters. 2. Overlapping chunks improve recall. 3. Metadata is critical for filtering and ranking. What is chunking in RAG? Chunking in retrieval augmented generation means splitting source documents into smaller retrievable units before embedding and storing them in a vector database. The purpose is to ensure each chunk is semantically coherent, small enough for precise retrieval, and large enough to contain meaningful context. Core chunking parameters. Chunking quality is mainly defined by size and overlap. Chunk size should be measured in tokens rather than characters. In practice, sizes range from 100 to 300 tokens for FAQs, 300 to 800 for technical documentation, and up to 1,000 tokens for long-form content. A reliable rule is to keep chunk size close to 1 or 2 times the expected answer length. Overlap is typically set between 10 and 30% of the chunk size to avoid losing context at chunk boundaries, especially in procedural or highly connected text. Fixed size chunking. Fixed size chunking splits text every n tokens with a predefined overlap. This approach is easy to implement and fast, making it suitable as a baseline. However, it often breaks semantic units such as sentences or sections, which can reduce retrieval quality. Sentence-based chunking. Sentence-based chunking groups full sentences together until a token limit is reached. This preserves semantic meaning and improves embedding quality, although it results in uneven chunk sizes. It works well for blogs, articles, and explanatory content. Paragraph-based chunking. Paragraph-based chunking splits text using natural paragraph boundaries such as newlines, markdown blocks, or HTML paragraph tags. This usually produces coherent chunks but can create very large chunks if paragraphs are long. A maximum token limit is commonly applied to control this. Structure-aware chunking. Structure-aware chunking leverages document structure such as headers, sections, and subsections. Markdown or HTML headers define logical chunk boundaries, aligning well with how users ask questions. This approach significantly improves retrieval quality for documentation, wikis, and knowledge bases, and is considered a best practice in production RAG systems. Sliding window chunking. Sliding window chunking creates overlapping chunks by shifting the token window forward by a fixed step. This strategy increases recall and reduces the risk of missing relevant context, but produces more chunks and higher storage and compute costs. It is useful when recall is more important than efficiency. Semantic chunking. Semantic chunking dynamically splits text based on topic changes rather than fixed sizes. Sentence embeddings are compared. and a split occurs when similarity drops below a threshold. This produces high-quality chunks, but increases ingestion complexity and processing time. It is often used in high-end or enterprise RAG systems. Hierarchical chunking. Hierarchical chunking stores multiple levels of granularity, such as section summaries, paragraph chunks, and sentence-level chunks. Retrieval can first identify the relevant section and then narrow down to finer chunks. This approach preserves global context while enabling precise answers and works especially well for large document collections. Metadata as part of chunking. Metadata should be attached to every chunk, including source document, section title, chunk identifier, and token count. Metadata enables filtering, re-ranking, traceability, and citation generation, and is an essential part of an effective RAG pipeline. Chunking for different data types. Different content types require different chunking strategies. PDFs benefit from paragraph-based chunking after cleaning headers and footers. Code should be chunked by functions, classes, or files without splitting logical units. Question and answer datasets usually work best when each Q and A pair is stored as a single chunk. Recommended default strategy. A robust default approach is to first split documents by structural headers, then apply sentence-based chunking within each section with a maximum of 500 to 800 tokens, include a 15 to 20% overlap, and store rich metadata alongside each chunk. Impact of chunking on RAG quality. Chunking decisions directly affect RAG performance. Chunks that are too large often lead to hallucinations, while chunks that are too small can miss necessary context. Poor semantic boundaries reduce relevance, and excessive overlap increases token and storage costs. LangChain classes for RAG. LangChain provides high-level abstractions for building RAG pipelines. Document loaders such as TextLoader, PipedFloater, and WebBaseLoader are used to ingest data. Text splitters like Recursive Character Text Splitter, Token Text Splitter, and Markdown Header Text Splitter handle chunking with structure awareness and overlap. Embeddings are generated using classes such as OpenA embeddings or Hugging Face embeddings, and vector storage is handled by integrations like Feis, Chroma, and Pinecone. Retrieval is performed through retrievers such as Vector Store Retriever or Multi-Query Retriever, which are then combined with LLMs using chains like Retrieval QA or Conversational Retrieval Chain. Llama Index classes for RAG. Llama Index focuses on indexing and retrieval abstractions optimized for RAG. Data ingestion is handled through Simple Directory Reader and other specialized readers. Chunking is controlled via node parser implementations such as Sentence Splitter, Token Text Splitter, and Markdown Node Parser. The resulting nodes are stored in an index, commonly Vector Store Index, with support for multiple vector databases. Retrieval is performed using retriever classes and enhanced with Query Engine or Chat Engine, which manage context assembly, ranking, and interaction with the LLM. Vector database. Embeddings are stored in a vector database optimized for approximate nearest neighbor search. Common tools include 1. Pinecone. 2. Weaviate. 3. Milvus. 4. Quadrant. 5. Feis. 6. OpenSearch with vector extensions. The vector store enables similarity search using cosine similarity, dot product, or Euclidean distance dot retriever. The retriever selects the top k most relevant chunks for a query. Advanced retrieval strategies include 1. Hybrid search, BM25 plus vectors. 2. Multi-query expansion. 3. Reciprocal rank fusion. 4. Metadata filtering. 5. Time-aware retrieval. Generator. The generator is typically an LLM such as 1. GPT-4 or GPT-4.1. 2. Claude. 3. Llama. 4. Mistral. 5. Mixtral. The retrieved documents are injected into the prompt, often using structured templates. Chapter 3. Prompt engineering for RAG. In RAG, prompt engineering is not cosmetic, it is architectural. A good RAG prompt. 1. Separate system instructions from context. 2. Clearly instructs the model to use only retrieved data. 3. Handles unknown answers explicitly. Typical prompt structure. 1. System rule, behavior and constraints. 2. Context block, retrieved documents. 3. User query. 4. Output format constraints. Key techniques. 1. Cite sources in output. 2. Use delimiters for context. 3. Penalize hallucination explicitly. 4. Enforce JSON or schema output. Prompt templates should be version-controlled like code. Chapter 4. RAG Design Principles. There are several non-negotiable principles when designing RAG systems. Principle 1. Retrieval quality beats model size. A smaller model with excellent retrieval often outperforms a larger model with poor context. Principle 2. Garbage in, garbage out. If your documents are outdated, duplicated, or poorly chunked, generation quality collapses. Principle 3. Latency is a system problem. Latency comes from 1. Embedding generation. 2. Vector search. 3. Prompt size. 4. Model inference. You must measure and optimize each stage independently. Principle 4. RAG is not search. Search retrieves documents. RAG synthesizes answers. Do not expose raw chunks blindly. Chapter 5. Advanced RAG techniques. Hybrid retrieval. Combines keyword search with vector similarity to improve recall on exact terms like IDs or error codes. R ranking. Use cross-encoders or LLMs to re-rank retrieved chunks for better precision. Ranking is the initial ordering of retrieved chunks based on their relevance to a query. In RAG systems, this usually happens during vector search, where chunks are ranked by similarity scores such as cosine similarity between the query embedding and document embeddings. The result is a list of top K candidate chunks. Re-ranking is a second, more precise relevance evaluation applied after initial retrieval. It takes the top K ranked chunks and reorders them using a stronger but more expensive model, such as a cross-encoder or an LLM-based scorer, which looks at the full query chunk pair. Re-ranking improves answer quality by pushing the most contextually relevant chunks to the top and filtering out semantically similar but unhelpful results. Not exactly. Ranking is not just a dictionary, though it can be stored as one. Here's the short, correct mental model. What ranking actually is. Ranking is an ordered list of candidates with relevant scores produced by a retriever. Conceptually, it looks like chunk _ 7, 0.82, chunk _ 3, 0.79, chunk _ 12, 0.74. Each chunk is assigned a score, for example cosine similarity, and the list is sorted from best to worst. You might store this as a list, array, or dictionary internally, but ranking itself means ordering by relevance, not the data structure. How the score is computed. During retrieval, the query is embedded and compared to stored chunk embeddings. Common scoring methods include cosine similarity, dot product, or Euclidean distance. The higher, or lower, depending on metric, the score, the more relevant the chunk is considered. How we choose the best one. There are 3 common selection strategies. On top 1 selection, you simply take the highest scoring chunk. This is fast but risky if that chunk lacks enough context. 2. Top K selection, most common. You take the top K chunks, for example the best 3 to 10, and pass all of them to the LLM. This balances precision and context coverage and is the standard approach in RAG 3. Re-ranked selection. You first retrieve top K using vector similarity, then apply a stronger model to rescore them. After re-ranking, you either take the top n chunks or apply a score threshold to discard weak results. Why we usually don't pick just one. A single chunk may be semantically close but incomplete. Multiple top chunks. 1. Reduce hallucinations. 2. Provide complementary context. 3. Allow the LLM to synthesize a better answer. Practical rule of thumb. Retrieve top 10 to 20 re-rank, keep top 3 to 5 send to the LLM. If you want, I can show this as a simple RAG flow diagram or a minimal Python example showing ranking and re-ranking step by step. Multi-hop RAG. Chain retrieval steps when a question requires multiple facts. Multi-hop RAG is a retrieval-augmented generation approach designed to answer questions that cannot be solved with a single retrieval step. Instead, the system performs multiple retrieval hops, where each hop uses information from the previous step to refine the next query. What problem it solves? Standard RAG works well for direct questions like, what is Kubernetes? Multi-hop RAG is needed for questions like which Kubernetes feature enables rolling updates and how does it reduce downtime. This requires first finding the relevant concept and then retrieving deeper, related information. How multi-hop RAG works conceptually. The system starts with the user query and retrieves an initial set of relevant chunks. From those chunks, it extracts key entities, concepts, or subquestions. These are then used to form a new query for the next retrieval hop. This process repeats until enough evidence is collected to answer the question. Typical multi-hop flow. First, retrieve high-level or overview chunks related to the query. Second, identify missing details or follow-up questions implied by those chunks. Third, perform another retrieval using refined or expanded queries. Finally, combine the evidence from all hops and generate the answer. Example. User question. How does Kubernetes rolling updates minimize downtime? Hop 1 retrieves general Kubernetes deployment concepts. Hop 2 retrieves a detailed section specifically explaining rolling update mechanics. The LLM then synthesizes the final explanation using both hops. How it differs from re-ranking. Re-ranking only reorders already retrieved chunks. Multi-hop RAG performs new retrievals, expanding the search space based on intermediate reasoning. Common strategies for multi-hop RAG. One strategy is query decomposition, where the LLM breaks the original question into smaller sub-questions. Another is iterative retrieval, where each hop uses the previous answer as context. A third is entity-based hopping, where detected entities or concepts trigger new searches. When to use multi-hop RAG. It is especially useful for complex why, how, and compare questions, for large or distributed knowledge bases, and for technical, scientific, or legal domains where answers are spread across multiple documents. Trade-offs. Multi-hop RAG improves reasoning and answer completeness but increases latency, cost, and system complexity. It requires careful hop limits and stopping criteria to avoid unnecessary retrieval loops. Practical guideline. Limit hops to 2 or 3, store evidence from each hop, and always combine multi-hop retrieval with re-ranking to keep only the most relevant chunks for generation. If you want, I can show a simple pseudocode example, or how to implement multi-hop RAG using LangChain or Llama Index. Tool calling RAG. Combine retrieval with 1. SQL queries. 2. APIs. 3. Code execution. 4. Knowledge graphs. Agentic RAG. LLMs decide. 1. When to retrieve. 2. What to retrieve. 3. How many times to retrieve. This enables reasoning-driven retrieval loops. Chapter 6. C/CD for RAG systems. RAG systems must be treated like ML plus backend plus data pipelines. Versioning. You must version 1. Embedding models. 2. Chunking logic. 3. Prompt templates. 4. Retriever parameters. 5. Vector indexes. Store all versions as metadata, not just in code. Versioning in RAG is done by treating every component as immutable and assigning explicit versions whenever anything changes. Documents are versioned using IDs and content hashes. Chunking strategies have their own versions based on size, overlap, and splitting logic. Embeddings are versioned by model and pre-processing, and any change requires re-embedding all data. Vector indexes are created per combination of document, chunk, and embedding versions and are never modified. Retrievers, re-rankers, prompts, and LLM settings are also versioned through configuration. All these versions are pinned together into a single pipeline version, which is logged with every generated answer to ensure reproducibility, traceability, and safe rollback. Continuous ingestion. C pipelines often include 1. Document change detection. 2. Re-embedding on updates. 3. Index refresh strategies. 4. Canary deployments for indexes. Deployment. Common stacks. 1. Dockerized retrievers. 2. Kubernetes for scaling. 3. Serverless inference for generators. 4. Feature flags for prompt changes. Infrastructure as code using 1. Terraform. 2. Pulumi. 3. Helm charts. Chapter 7. Testing RAG systems. Testing RAG is fundamentally different from testing traditional software. Unit tests. 1. Chunking logic. 2. Metadata extraction. 3. Retriever filters. 4. Prompt formatting. Retrieval tests. On. Recall at K. Recall it K measures how often the system retrieves all relevant documents within the top K results. Did we retrieve the information we needed? 2. Precision at K. Precision at K measures how many of the retrieved top K documents are actually relevant. How much noise did we retrieve? 3. Coverage metrics. Coverage measures whether the retrieved chunks collectively contain all the information needed to answer the query, even if no single chunk is sufficient on its own. 4. Query document alignment. Query document alignment measures how well retrieved documents semantically and contextually match the intent of the query, not just keyword overlap. Generation tests. On. Faithfulness. 2. Groundedness. 3. Hallucination rate. 4. Citation accuracy. Regression testing. Use fixed evaluation datasets and compare outputs across 1. Prompt versions. 2. Model upgrades. 3. Index changes. Human-in-the-loop evaluation. Critical. 4. 1. Safety. 2. Tone. 3. Domain correctness. Tools commonly used. 1. Langsmith. 2. Ragas. 3. TrueLens. 4. OpenAI evils. 5. Custom golden datasets. Chapter 8. Monitoring and observability. Production RAG systems must be observable. Key metrics. 1. Retrieval latency. 2. Context size. 3. Token usage. 4. Cost per query. 5. Answer confidence. 6. Fallback rate. 7. User satisfaction signals. Logs should include 1. Query. 2. Retrieved chunk IDs. 3. Prompt version. 4. Model version. 5. Output hash. This enables post-mortem analysis of failures. Chapter 9. Security and data governance. RAG systems often expose internal knowledge. Critical controls. 1. Role-based document filtering. 2. Tenant isolation. 3. PII redaction. 4. Prompt injection protection. 5. Output sanitization. Never blindly trust retrieved documents. Chapter 10. When not to use RAG. RAG is not always the right solution. Do not use RAG when 1. The domain is small and static. 2. Low latency is critical. 3. Deterministic answers are required. 4. Strong transactional consistency is needed. Sometimes fine-tuning or traditional search is better. Closing thoughts. Retrieval-augmented generation is not about making models smarter. It is about making systems more reliable. RAG shifts intelligence from model weights to system design. In production, success depends less on which model you choose, and more on 1. Retrieval quality. 2. Data hygiene. 3. Evaluation rigor. 4. C/CD discipline. 5. Observability. RAG is not a feature. It is infrastructure for knowledge-driven AI systems.